How's it going, everyone? Mr. Geyser here with the final video in our Lesson 13B series, where we'll be taking a look at properties of exponential inequalities and properties of logarithmic inequalities. In these first two examples here, or the first two parts of example 16 here, we want to take a look at these two properties, where first, if b, the base of an exponent, is greater than 1, then the exponential function y is equal to that base of x is increasing over all of those x values, where we can state that this means that b raised to the power of x is less than b raised to the power of y if and only if that x value is less than that y value. Let's explore that first property there in part A. We'll explore that second property in part B. First, in part A, we're going to find the solution set of the inequality stated in part A. We want to check for extraneous solutions and verify our answers using a graphing utility, where in this case here, we will be using Desmos to verify our answers. In this first section here, I'm actually going to rewrite this here as x raised to the power of x is greater than 125 raised to the power of x plus 6. I want to try and manipulate this like we did in those first videos in lesson 13, where I want to try and change the base of this second exponential function to have that same base of 5. I can do that because 125 there happens to be a factor of 5. All I'm really converting is that 125 into 5 raised to the power of 3. That 5 raised to the power of 3 and that 125 are perfectly equivalent, where whenever I have some exponent inside of those parentheses raised to another exponent, all I'm really doing is multiplying that internal exponent of 3 into the other exponents. That's one of our exponential properties from like unit 11 or unit 2.11, where that topic there showed us these exponential properties are distributed if there's an exponent of an exponent. So now we have the same basis. 5 raised to the power of x is greater than 5 raised to the power of 3x plus 18. And we can just cross both of those 5's out, and we know that b, this x here is greater than our y of 3x plus 18. Notice how since the b base is greater than 1, this property here states that our values here stay on the same side with our inequality not flipping. We just bring those exponents down, and these stay the same. In part B, that's going to change. But keep that in mind. If the base is greater than 1, it is increasing continuously, we are able just to bring those exponents down and make it into this inequality. I now bring that inequality over here, and I just solve for x like I know you guys know how to. I'm subtracting 3x to both sides. I divide by -2, and when I divide by -2 is when my inequality here flips, and I get x is less than -9. It only flips here because I happen to divide by a negative. If I divide or multiply by a negative, my inequality flips to get x is less than -9. Well, let's prove this answer graphically using Desmos. In Desmos here, I've already prepared these two functions, where f of x is equal to that 5 raised to the power of x, and g of x is equal to 125 raised to the power of x plus 6. And it's really hard to see when these two lines cross, or it's really hard to see when these lines are above each other. I want to see when that blue line there is above that red line. And to me, it doesn't look like it ever is above. But what we can do is be a little bit clever on the scale in which we look at using our y value, or our y-axis. What I mean to say is, instead of changing our y scale in a linear way, where it's increasing by 10, or it's decreasing by 10, or it's increasing or decreasing by 100, let's change the scale logarithmically. What we do is in Desmos here, if we click on that settings option and we scroll down to more options, we're given this option here to change our y-axis to a logarithmic scale. When we do this, our scale now changes from 1, 2, 3, 4, 5 to being 1, 10, 100, 1,000, 10,000, 100,000. It's now in the multiples of 100, in multiples of tens. And now, when I scroll down, I get these two functions here look pretty linear. So, when we change the y-axis to be logarithmic, our exponential functions look linear. I'll repeat that. when we change our y-axis to be logarithmically scaled, our exponential functions look linear. When we have these linear-looking exponential functions, it's easier for us to zoom in and see that at exactly -9, the blue graph here is now larger than that red graph there. Let me change that y or that x-axis there so it's a little bit easier for us to see. Let's make that -20, and let's just go to -5. Now, when we go down to this here, it's a little bit easier to see that that blue graph, that 5 raised to the power of x, is greater than that red graph, that g of x there, at -9 only. Past -9, it changes. So we can state on our guided notes that 5 raised to the power of x is greater than 125 raised to the power of x plus 6 when x is between -infinity and 9, where we do not include 9. At -9 is when they intercept. So at -9, we need to exclude it because that's when our red graph of g of x is now equal to our blue graph of f of x. We just want to see when f of x is greater than our red graph. As a quick note, in the future part of these slides, I end up messing up writing these problems here of f of x and g of x, so you'll see that mistake coming up. But let's take a look at that second property. That second property for exponential inequalities states that if our b value, our base, is in between 0 and 1, then the exponential function y equals b, that base to the power of x, is decreasing across all of our x values. So it's constantly decreasing over time. This means that when b of x is greater than b of y, if and only if x is smaller than y. Notice how these properties are reversed. See how when b is greater than 1, the inequality stays the same. But when b is in between 0 and 1, it's a decaying function, so the inequality is going to flip. We'll see that now in part b. In part b, we're given that 1/3 raised to the power of 2x plus 9 is less than or equal to 1/27 raised to the power of x minus 3. First, when I rewrite this, there's those mistakes again. First, when I rewrite this, I'm able to try and convert this base of 1/27 into 1/3. I want to try and solve for x here. I know that 27 is just going to be the third exponent of 3. So I can actually write 1/3 raised to the power of 3 raised to the power of x minus 3. And I can use that same trick that we did before, where I'm just distributing that 3 into those upper exponents to get 1/3 raised to this power is less than 1/3 raised to the power of 3x minus 9. So I'm using those exponential properties we learned from previous topics in this step here. Now, when I get rid of these bases here, since the base is less than 1 but greater than 0, notice that this inequality here flips. It now changes because property 2 states that the base is in between 0 and 1. The inequality flips. Now we want to try and solve that normally as we would with any kind of inequality here. Where we're going to subtract 2x to both sides. We're going to add that 9 to both sides. And we end up getting 18 is greater than or equal to x. This here is our solution for this inequality. So let's test that out. In Desmos here, let me prepare Desmos so we have these two graphs. Now with the graphs prepared on Desmos, we can take a look and see that f of x is still equal to 1/3 raised to the power of 2x plus 9, and our g of x is now equal to 1/27 raised to the power of x minus 3. And we want to see specifically at what point does this blue line here happen to start or happen to be greater than that red line there. Now in general, we can clearly see that this blue line is larger than this red line here for most of this graph. But somewhere at 18 here, is it going to cross? And we could try and zoom in closer and closer to 18 here to try and find exactly when it crosses here. But we keep zooming in and it doesn't ever look like it crosses over. But instead of us zooming in, I'm going to go back to home here. Let's use that same trick where we're going to change this y scale into a logarithmic scale, no longer a linear one. To do that again, we're going to go to our settings, going to that more options here, and selecting logarithmic. And now our scale factor here is going by multiples of 10. So when we're going up in value, it's really easy for us to see we're going from 1 to 10 to 100 to 1,000 to 10,000 to like 100,000 up to like a million up here. But when we're going down in scale, think about us shrinking smaller and smaller. So we're starting at 1, we're going down to 0.1, we're going down to 0.01, 0.001, and we keep shrinking smaller and smaller and smaller. It's not that we're going into the negatives. It's that this here is now increasing the number of zeros after that decimal point. So as we shrink down, we want to try and find right at 18 that it crosses here at 18, 3.38 times 10 to the negative 22. That's like nanometer small, incredibly small. But that's when it does cross. Everything after 18, that red graph of x, or sorry, 1/3 raised to the power of 2x plus 9 is greater than our blue graph there. Our blue graph is only greater when it's 18, or when it's right before 18, not exactly 18, or less. The last thing I want to point out with these exponential functions, of course they're linear because we changed that y-axis to be logarithmic, but they're both decreasing. Because that base there is less than 1 but greater than 0, both of these graphs here are now decreasing. That also changes that inequality there to be flipped around when we're solving it. But graphically, we know that both these lines are going smaller over time. When we bring this information back into our graph here, we want to state that this inequality is less than this, this exponential function is less than this second exponential function when x is equal to negative infinity all the way up to and including 18. We're including 18 because we have that equals underneath our inequality there. We're redrawing it here where that x value is still 18 and that y value is that incredibly small y point, where our x is still in a linear form and our y is now in logarithmic scales. That was our first two properties for our exponentials. Now let's take a look at this next example where we explore 3 different logarithmic examples. In example 17 here, we have 3 logarithmic inequality properties that we want to explore. First, if b is greater than 1, then log base b of x is greater than log base b of y if x is greater than y. This is also true for less than or equal to, or greater than or equal to. For that property 2, if that b value is in between 0 and 1, that log base b of x is less than log base b of y if and only if the x value is larger than y. It's almost like it's another decay there. Finally, if our base is still in between that 0 and 1, for our log base b of x is greater than our log base b of y, then our x is less than our y value here. This is also true for that less than or equal to here. Or sorry, or greater than or equal to here. We'll explore these 2 examples here, 2 and 3 in B and C, but let's explore that first property in part A. In part A here, we want to find the solution sets for these inequalities and then check for extraneous solutions and verify our answers using that graphing utility of Desmos. In part A here, we have the log base 2 of 9 is greater than 2 times log base 2 of x. I'm just going to rewrite those logs there, and I want to try and manipulate this 2 into that x first, getting rid of that product there pretty quickly. That way I have log base 2 of 9 is greater than log base 2 of x squared. Since my log base 2 are the same, I can remove both of those logs and just say 9 is greater than x squared. And since my base is larger than 1, this inequality does not change. I'm now able to solve this out where the square root of both sides here gives me plus or minus 3, where I don't know if it's negative 3 or positive 3. But I can plug in that negative 3 and positive 3 back into my question or my problem here and determine which one of these are extraneous. I know that when I plug in that negative 3, I'm going to get some negative input into the log, which creates a non-real answer. So the only answer here is going to be 3. However, this is going to be the upper limit for our range, or sorry, for our domain here. Our lower limit is when the internals of the log here is equal to 0. In our case here, this equals to 0 when x happens to equal 0. We have that lower limit of 0, not negative, but we will need to solve for this lower limit later on in our problems here. Let me set up Desmos to showcase these two graphs now. In Desmos, I've set up g of x for us, but I want to try and showcase to you guys how we're creating a custom log base in Desmos for f of x. In f of x, we want to try and write out log base 2 of 9. If we just type in log here, there's no easy way for us to create a log base 2 just from typing. So what we need to do is we want to open up the keyboard function in Desmos. We want to go over to where it says functions here, and we want to scroll down until we find calculus. For calculus here, it gives us exponents, natural logs, logs, but specifically we want that log custom base, where that custom base there is going to give us 2 of 9, which is just going to give us a straight horizontal line at that like 3.16993 decimal. And now when we determine when these two intercept is when these graphs here are either greater than or less than each other. And it's really easy to see that that f of x is greater than g of x here everywhere before 3, where we do not include 0 or anything behind 0 because it's not in the domain of g of x. However, I want to show you guys what happens when we change the scale of our x-axis to be logarithmic. When we looked at exponential functions and changed the y scale, those exponential functions turned linear. When we have logarithmic functions and we change the x scale to be logarithmic, those graphs should then be linear. Let's showcase this. We go to our settings. We're scrolling down to more options. And my x-axis here, I'm changing to logarithmic. And look at what happens to our log function. Our log function now looks like a linear line. That horizontal is still a horizontal. It's still just a straight line. But that once curved log line is now a linear line. It's still intercepting at that specific point there, but that log base is now going in that y from positive to negative infinity, where that x is limited from that positive, or x is limited at 0 up to all the positives. We can't actually scroll back past our negative value here. It just creates that 10 raised to the power of some greater negative value. So we're limited to just the positive x values when we change our x-axis to be logarithmic. When we demonstrate this here on our guided notes, we're just trying to describe that log base 2 of 9 is greater than 2 times log base 2 of x when x is between 0 and 3, where we do not include 0 because it's not in the domain of g of x, and we don't include 3 because we're just trying to determine when that first function is greater than, not greater than or equal to. When we draw this out here, we have our x-axis log scaled and our y-axis as normal, intercepting at 3 there. We want to try and showcase that that red graph for the f of x goes into the negative, but that blue graph there does not go into the negative because it's not in the domain of that blue graph. Let's take a look at property 2 when we take a look at part B. In part B here, we're given log base 2 of 2x plus 1 is less than or equal to 3. In that problem, when I rewrite it, I want to try and manipulate this in some way where I'm solving out the internal of 2x plus 1. Remember, when we have some log function there, we could raise this to the power of 2 to both sides to try and remove that log base 2. But really, all that's doing is we're using that rock and roll method to get 2 raised to the power of 3 is greater than or equal to 2x plus 1. When we use that rock and roll method, the inequality stays the same. It's still less than or equal to 2 raised to the power of 3, where that base of 2 is now the base of the exponent for 3. That 2x plus 1 is still on the left side of the equation. Our base of 2 is still some positive number that's greater than 1. So when we're solving this out here, we just need to try and manipulate that 2 raised to the 3 is now equal to 8. We now can subtract 8 to both sides, or subtract 1 to both sides, and we get 2x is less than or equal to 7, divide by 2, and we get x is less than or equal to 7 divided by 2 for that fraction. What we want to try and highlight in this specific example is that this here is clearly the upper limit of our interval. What we need to try and find now is the lower limit of our interval. Initially, we would say it's 0, but it's not exactly 0 because the lowest input isn't 0. It must be solved for this lower input. What I mean to say is that when we plug in 0 into this problem here, we get 2 times 0 to get 0 plus 1, which is log base 2 of 1. There's still lower input values that we can plug in to get some lower log here. So what I mean to say is we found the upper limit for this interval here. We now need to find the lower limit of this interval by solving the internal of that log base 2 to equal 0. To do that, we're just taking out that 2x plus 1 here and solving for 0 here. We're doing this intuitively. The reason why we're solving for 0 here is we want to find the lower end of this limit here. In the case that this was x is greater than or equal to 7 over 2, we wouldn't need to solve for that because that would be then the lower limit. But since it's x is less than or equal to 7 over 2, we still need to find the lower limit. To find the lower limit is when the internal section of this log here is equivalent to 0. It's equivalent to 0 when x there happens to equal -1/2, or we can describe that interval there as -1/2 comma 7 over 2. Well, let's test that out graphically on Desmos. Let me set up Desmos real quick for us to observe. With Desmos now set up, we're able to take a look at this f of x, which equals that log base 2 of 2x plus 1, and g of x, which equals that horizontal line at 3. Notice that the graph here is now shifted horizontally 1 unit to the left because internally it has that horizontal translation. For that horizontal translation, it's shifted over 1 unit where its new vertical axis, or its new vertical asymptote is at -1/2 when the internal section of that is equal to 0. We want to try and explore this graphically using that different log base for our scale factor and our x. We can do that by just changing that scale factor here. We're going down to our more modes and we change this to logarithm. Notice that we can't go into the negatives when we do this scale. So when I do this scale here, it now forces this negative here, or this graph here, to only be looking at the positive sections. If I want to manually try and change this x value here to be like -1 or 0.5 here, Desmos will not allow me to do this. In a logarithmic scale, it only goes from 0 to positive infinity. In that y value there, if we change that to logarithm, it would only go from 0 to positive infinity. It doesn't look at the negative values when you change the scale of it. But notice what happens when we do that. We still have that intersection here at 3.5, 7 over 2. But when we go more closer to that negative realm, our logarithmic function that once looked linear here on the upper end, it creates like a horizontal asymptote as we get closer and closer to 0. It's just a unique feature of these scaling factors that we use for this here. But if you want to explore this more, I'd love for you guys to try and explore how far down Desmos goes for our x values. But it will never, ever go into the negative realm. To look at the negative realm here, we do need to go and make this into a linear function and just rationalize that the lowest input for our domain of our f of x is that -1/2 because of the new horizontal or the new vertical asymptote. When we bring that information back into our guided notes here, what we're really trying to describe here is that between -1/2 and 7 over 2 is when log base 2 of 2x plus 1 is less than or equal to 3 here. For this here, it should be a bracket instead of a parenthesis for that input there. My bad. It should be a bracket here where it includes that 3 there. That was my mistake. So this here should include it because it's that point that we are including. When we draw this graph out, we really don't ever draw our log graphs into the negatives. Now that we're finished with part B, let's move on to the final part of lesson 13B. In part C, we are given log base of 1/2 of 2x minus 3 is greater than or equal to log base of 1/2 of x plus 5. In general, step by step, we're given this function here. We want to try and prove what x values make that first function there greater than that section function. First, we have the same log base. We simplify that one out. Second, the inequality flips because the base is in between 0 and 1. Just like our exponential functions, since the base of our log, or the base of our exponent, is less than 1 but greater than 0, when we use that property of equality for logarithms or exponential functions, the inequality flips. Now that we have those inequalities there, or now we have that inequality there, our next step there is just to solve for x. Easy solve here. We now just add 3 to both sides, we subtract x to both sides, and we end up with x is less than or equal to 8. Now, we want to try and plug that back into these problems here and determine where the extremities are. In this case here, we have no extremities. We just have one solution. But now we need to determine what the lower limit is. For the lower limit, we want to look at when this here is less than 8. So when we're looking at the less than 8 there, we're taking a look at which one of these internals that we need to solve for. And it's going to be when this internal here is equal to 0, because that's what we're taking a look at. So when we have that internal there less than 0 there, we want to try and solve it to find when x is greater than 3 over 2. The reason why we want to determine when this internal here is 0 is because it's the log base is less than 1. We found the upper limit because x is less than 8. So we go back to our original problem there and solve for 0 on the inside of that first function. We solve for x when log base 1/2 is 2, or when log base 1/2 of 2x minus 3 is greater than 0 because the function is decreasing but is above that first function of log base 1/2 of x plus 5 on the lower end of this. Let me set up Desmos to try and showcase this. Let's take a look at these graphs on Desmos now and see when that f of x there in red is greater than that blue g of x here. We can see that the red graph is larger than the blue graph on the lower end of these scales here, but it's kind of difficult to see when these happen to cross. Luckily for us, we can identify that that point there is at 8, negative 3.7, but when we change our x scale here into a logarithmic scale, it's very easy to see these two graphs here change to that linear function. We go to that settings here, going down to that more option, changing our x-axis here to logarithmic, and notice what happens to our functions here. This function here still crosses at x, negative 3.7, but because we're using a logarithmic scale that doesn't show the negative values, where both these f of x and g of x actually go into the negatives there, we don't see what happens on the left end of our y-axis. Notice that for f of x though, f of x does have a vertical asymptote at like positive 3 over 2, or 1/2. So at 1/2 here, the graph doesn't go further than x equals 1.5. It doesn't go past that. So when we go to this direction here, the graph here ends. So that lower limit, when f of x is greater than this blue graph here, is at its horizontal or at its vertical asymptote. When we describe that inside of our guided notes here, we want to try and specify that our lower limit is going to be 3 over 2, 8, where we include 8 because it is equal to each other at that value of 8. When we demonstrate this here, make sure to not include your graphs on the left side of our y-axis. And that intersection there is when both of those graphs are equal to each other and crossing. In these examples here, we explored these solutions of logarithmic and exponential inequalities and solved when those intervals for the domain showcase those answers. We then used Desmos to graphically change the scale in our x and our y-axis to double check our answers. Thank you all for watching these videos here for Lesson 13A and B, and I look forward to seeing all of you guys in class. Take care.